Okay, welcome back. Yesterday, this was a homework problem for us. Yes. Yes, beta. So, what is the answer? Some of your friends had answered rightly. Yes. Option A is answer. Very good. Okay, beta. See here. Let us proceed further. Let us start our discussion here. So, find H at the center of the square loop of current I amperes flowing in a clockwise in Z is equal to 0 plane with side D. Yes. Just a minute, beta. Yes. So here it is a square loop of side D. Okay, beta. Here is a square loop. Current is flowing like this. How much is the current flowing? I amperes. I amperes. How much is the side of this one? Side of this one is D meters. Okay. Side of this one is D meters. What is the magnetic field? He is asking at the center, beta. Geometric center. Here. So how do you find out the magnetic field at the geometric center? What I'll do, I'll find out the magnetic field due to the each section and I will multiply with the number 4. Why like that? Suppose if the current is flowing like this, what is the direction of the magnetic field? It is like this. Here it is like this. Here it is like this. Here it is like this. So magnetic field at the center will going to add up. So what I'll do, I'll find out the magnetic field due to the each section and I'll multiply with the number 4. I'll going to turn the page here. Okay, beta? So I'll find out the magnetic field at the center, beta. Clear? So what is the angle and what is the side of this one, beta? The side of this one is D. And what is the angle made with respect to the corners here? Distance from here to here is D by 2. Okay. What is the angle made with respect to the corners here? This corner and this corner. How much is this angle? It is pi by 4. This angle is also pi by 4 beta. Clear? So I'll find out a magnetic field due to the each section. Hs is equal to I by 4 pi rho into sine alpha 1 plus sine alpha 2 beta. Clear? Done. So what happens to this one? Just substitute, just we are interested only in the magnitude. So the magnetic field due to the each side is I by 4 pi rho. What is the perpendicular distance? Is D by 2. Sine alpha 1 is sine 45 degrees plus sine 45 degrees. So which is Hs is equal to I by 2 pi d. Here it is 2 by root 2. So here it is I by root 2 pi d beta. Then what is the total Ht? 4 into Hs, which is 4 into I into root 2 pi d. So H total is equal to 2 root 2 I by pi d. Yes. That is the thing. So option A is the answer beta. Two root 2 I by pi d. Okay. Now what I'll do, I'll going to give some ready-made formula here. Let me turn the page, which will save our time. Suppose if you want to find out the magnetic field for n equal sided polygon beta, there is a ready-made formula. Note. For n equal sided polygon, for n equal sided polygon carrying current I amperes with side D, the magnitude of magnetic field intensity magnetic field intensity at the geometric center is H is equal to Ni by pi d tan 180 by n sin 180 by n. This is a ready-made formula. So this is for n equal sided polygon carrying the current I amperes with side D. Okay. So these are H. Units are ampere per meter. Let us take some examples here. Okay. Yes, beta. See here, this is a ready-made formula which will going to save our time. Fine. Now let us take some examples to appreciate this one. Let me turn the page here. Example number 1, beta. If I take n is equal to 3, what it is? It is an equilateral triangle. Yes or not? So that means there is an equilateral triangle like this. Here, current flow is I. I amperes. It is having a side D beta. I want to find out what is the magnetic field at the center. What it is? H is equal to, you can go by formula 3I by pi D tan 180 by 3 sin 180 by 3. So here H is equal to 3I by pi D. Tan 60 is root 3 beta. This sin 60 is root 3 by 2. So here it is H is equal to 9I by 2 pi D. Units are ampere per meter. Let us take one more example beta. Example number 2. N is equal to 4 beta. N is equal to 4 is nothing but a square, which we already done. But let me cross check with the help of this formula beta. Okay. See here. Here is the thing. How much is the current flowing? I amperes. What is the side of this one? Side of this one is D beta. So what happens to the H? H is equal to 4I by pi D tan 180 by 4 into sin 180 by 4. H is equal to 4I by pi D tan 45. This one is 1. This is 1 by root 2 beta. So here H is equal to 2 root 2 I by pi D. Units are ampere per meter. Next, example number 6. This C1, this we already got, isn't it? Directly also. 2 root 2 I by pi D beta. Clear? Yes. Let us take one more example. Example number 3 beta. N is equal to 6 beta. This was one of your gate question for 2 marks. Okay. So that means it is a hexagonal like this. 1, 2, 3, 4, 5, 6. How much is the current flowing? I amperes. How much is the side? D meters. So the H is equal to 6I by pi d tan 180 by 6 sin 180 by 6. So how much is this? H is equal to 6I by pi d. Tan 30 is 1 by root 2. Root 3, sorry. This is 1 by 2. Here it is root 3 I by pi d is the answer. So by remembering this formula, you can deal with any hexagonal. You can find out the magnetic field at the center. Clear? Yes. So now let us have one more question here. So yesterday we have seen the formulas for finite length conductor as well as for the infinite length conductor. This is the formula for the finite length conductor beta. Isn't it? And this is if you modify that one, you're going to get it for the infinite length conductor. Clear? So these questions are related to the finite length conductors. Fine. Let us have one question on the infinite length conductor. I'm going to turn the page here. Okay. Now let us have one more question. A long conductor carrying a DC current of 10 amperes in positive Z direction is located at x is equal to 3 meters, comma, y is equal to 4 meters. Find H vector. Find H vector. Find H at the following points. Question A 0, 0, 0. Question B 4, 5, 6. Question C 8, 8, 8. So here, observe this one carefully. A long conductor, that means it is a very long length. Yes, so it is an infinite length. So a long conductor carrying a DC current of 10 amperes in positive Z direction is located at x is equal to 3 meters, comma, y is equal to 4 meters. Find H at the following points. Clear? Observe this one carefully, beta. Yes. So where this infinite line current is located, let me draw the coordinate system. Here it is x-axis, here it is y-axis, here it is z-axis. Where this infinite line current is located, x is equal to 3 meters. 1, 2, 3. Y is equal to 4. 1, 2, 3, 4. Let me make some box out of this, beta. This is how this infinite line current is located. Somewhere here. So in which direction the current is flowing? Like this. How much is the current beta? 10 amperes current. What is this point beta? Here it is 3, 4, 0. What is this point? 3, 4, Z. Yes or not? What is changing on the line? Z value is changing. We have done the same thing when we are dealing with what is called infinite line charge. Here also something similar. But here it is current. There that was a line charge. So I want to find out the electric, this one. Let us consider some point here. This point is, let us say 8, 8, 8. 8, 8, 8. This is 8, 8, 8. Somewhere here 8, 8, 8. 8, 8, 8. If I drop a perpendicular from here to here, okay, so I'll take the perpendicular vector from here to here. Here is a rho is a perpendicular vector. This is a perpendicular vector. For this one to happen, this one happened to be a perpendicular vector. What must be this point beta? This point must be 3, 4, what must be the Z value? They must be of the same height. If they are at the different height, that will not correspond to the perpendicular distance. So they must be of the same height means what? If this is a perpendicular distance, then that must be, Z value must be 8. Yes. So in our terminology, we are calling this as a what? Field point, FP. This we are calling it as what? Source point, SP. Yes or not? Yes, very good. See, let me go back here. Some of your friends are asking. Here we are finding only the magnitude. Doesn't matter whether it is a clockwise or anti-clockwise. The magnitude will be same. Come back to this question. Okay. Now, let me turn the page here. What is the magnetic field due to the infinite sheet beta? Infinite line. B is equal to mu into I by 2 pi rho into current direction cross unit vector. So B is equal to mu naught into I divided by 2 pi rho into current direction is Z cap cross unit vector is rho cap. B is equal to mu naught into I by 2 pi rho into Z cap cross vector by its magnitude beta. Okay. So what happens to this B? B is equal to mu naught into I divided by 2 pi into Z cap cross rho vector by its magnitude square. That is the thing. Let us consider the first part of the question. What is the field point where I want to find out? At 0, 0, 0. So I want to find out the perpendicular distance vector, source point, 3, 4, Z beta. And I want a perpendicular vector from here to here. Let me call it as a rho 1 vector. To get a perpendicular vector, I should maintain the same Z value in this problem. Clear? So what happens to the B1? B1 is equal to mu naught into I divided by 2 pi. Here it is Z cap cross rho 1 vector divided by rho 1 magnitude square. Just substitute all the values here properly. So mu naught into, did I ask for H vector? Yes, beta. I asked for H vector. So if it is for the H vector, just remove. What is the H vector? H vector is equal to I by 2 pi Z cap cross rho vector by rho magnitude square. So what is the H1 vector, beta? H1 vector is equal to I by, what is the height? 10 amperes. 10 by 2 pi into Z cap cross rho 1 vector. What is the rho 1 vector? First, let me write down the formula. I by 2 pi into Z cap cross rho 1 vector by rho 1 magnitude square. Clear? So just substitute here. I is 10 amperes, beta. 10 by 2 pi into Z cap into 0 minus 3. It is minus 3x cap. 0 minus 4. It is minus 4 y cap divided by its magnitude is square root of 9 plus 16 whole square. Here it is x cap, here it is y cap, here it is z cap. Yes, so here H1 is equal to how much is this, beta? Here it is 10 divided by 2 pi into 25 into z cross x is y. Here it is minus 3y cap. Z cross y is minus x, so it is plus 4x cap. So here it is H1 is equal to 1 by 10 pi 4x cap minus 3y cap. Units are ampere per meter. Like this, you can deal with the second part of the question and third part of the question. But let me do that one. I'll going to turn the page, beta. Clear? Let me turn the page here. Second part of the question. What is the field point, beta? 4, 5, 6. Here it is 4, 5, 6. What is the source point? 3, 4, z, beta. I want to get a perpendicular distance vector. Here it is rho 2. To get a perpendicular distance vector, I should maintain the same z value here. Bas khatam. Now the rest of the thing is you can do. So what is H2 here? H2 is equal to I by 2 pi rho. I'll directly write 10 by 2 pi into current direction is z cap cross vector. Perpendicular vector is 4 minus 3. Here it is x cap plus y cap divided by its magnitude 1 plus 1 whole square. So here it is H2 is equal to 5 by 2 pi What is Z cross X beta? Z cross X is Y. What is Z cross Y beta? Is minus X. So this is the expression. Now let us take the third part of the question. What is the field point? 8, 8, 8. That is what we have taken as an example, isn't it? So to get a perpendicular distance, I should maintain the Z value as a 8 on the line charge, on the line current. So here it is. Source point is 3, 4, Z beta. Here it is a perpendicular distance, rho 3 vector. To get a perpendicular distance vector, I should maintain Z value same. So here it is. H3 is equal to 10 by 2 pi. Z cap cross product with 8 minus 3 is 5x cap. 8 minus 4 is plus 4y cap. Divided by square root of 25 plus 16 whole square. So here H3 is equal to 10 by 2 pi into here it is 41 into 5y cap minus 4x cap. That is the story. Clear? Fine. So we have done the numericals on finite length conductor, infinite length conductor, and even on the what is called a hexagonal beta. Fine. So let us have one more formula here. What is called a magnetic field due to the circular loop. This is also important. Clear? I'll go into turn the page here. Let us have a circular loop, and after that 5 pi. Where is that 5 pi? Okay, here it is 5 pi. Thank you. This is correction. Okay, let us have one more numerical beta. One more formula. Fine. Magnetic field due to the circular loop. Magnetic field due to circular loop, which is carrying the current I amperes. Clear? Yes. Now observe here, beta. Let us consider a coordinate system like this. Here it is x-axis, here it is y-axis, here it is z-axis. Clear? So what I'm going to do, I'm going to take this circular loop in the xy plane. I'm going to place this circular loop in the xy plane. Okay, here is the thing. And the current is flowing like this. And the radius of this one is A. And how much current it is flowing? I amperes. The current is flowing like this. If I put my thumb in the direction of current flow, my fingers will going to show the direction of magnetic field. I'll go away from this one at a distance of B. I'll go away from the center at a distance of B. I want to find out the magnetic field. Okay, let me use some other color which is not visible properly here. So at a distance of B, I want to find out the magnetic field. So if I put my thumb in the direction of current flow, my fingers will going to show the direction of magnetic field. So what would be the direction of magnetic field? The magnetic field direction is like this. Let me use some other color. Remember, just I'm taking away from the center. I'm going to represent it as a BZ. Actually, the overall magnetic field would be like this. We are finding only here beta, not here, 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 here. Okay, what is required is only at that point. Okay, if I put my thumb in the direction of current flow, my fingers will show the direction of magnetic field. Clear? Yes. If the current flow is like this, then the magnetic field would be downwards. Excuse. If I draw this one, if I redraw this figure for our visualization, it is something like this. This is a scenario. Okay. Here it is A. Here to here it is B. What is the magnetic field? Here it is. Current is flowing like this. The magnetic field here it is like this. Here is BZ. Clear beta? Yes, that is how the scenario is. I'll not going to do any derivation here. But the idea here is, first you need to find out the B. How do you find out the B? You need to find out the magnetic field due to a small piece of current element, and later you need to perform what is called a integration from 0 to 2 pi. That is the technique here. Fine. But ultimately what you need to remember for your exam is a formula. But how you will get that formula? From this expression. What is the expression? B is equal to mu by 4 pi line integral of IDL cross R cap by R magnitude square. Okay. So you need to integrate this one from 0 to 2 pi beta. Clear? So what happens to this one? So here it is. B is equal to mu into I into A square into Z cap divided by 2 into A square plus B square to the power of 3 by 2. This is a formula which is need to be remembered. Mu into I into A square into Z cap by 2 into A square plus B square to the power of 3 by 2 beta. Clear? Yes. Now you need to remember something special cases. Two special cases of this one. I want to find out what is the magnetic field at the center of the circular loop beta. Okay. Let me turn the page here. So case number 1. Let us try to get the two cases from there. Case number 1. At center. I want to find out the magnetic field at the center. That means what should I do? I should make B is equal to 0. Clear? Yes. So I should make here B is equal to 0. If I make B is equal to 0 in that formula, here it is. B is equal to mu into I into A square into Z cap divided by 2 into A square to the power of 3 by 2. So this will become mu into B is equal to mu into I into Z cap divided by 2 into A. Units are Weber per meter square. This is a modified formula for what? At the center of the circular loop. And you can even find out the H vector. What is H vector here? I by 2A into Z cap. Units are ampere per meter. Let me go back. What is H beta? H is equal to I into A square into Z cap divided by 2 into A square plus B square to the power of 3 by 2. Okay. Now let us consider the two other extreme case. This is at the center of the circular loop. In the second case, what I'll do, I'll go far away from the circular loop. I'll go to the very far away distance. Okay. Case 2 beta. Far away from center. Far away from the center means it is like this. This is the radius is A. From here to here, the distance is B. So here B is far greater than A beta. So what happens to this one? What is approximation can be done? This A square plus B square is approximated to B square. So what is this B? B is equal to mu into I into A square into Z cap divided by 2 into A square plus B square to the power of 3 by 2 is approximated to mu into I into A square into Z cap divided by 2 into B square to the power of 3 by 2. So the B is equal to mu into I into A square into Z cap divided by 2 into B cube. Its units are Weber per meter square beta. Clear? Yes. So especially you need to remember this one, mu I by 2a. Clear beta? Let me turn the page here. I'll going to take one example so that it will clarify all your doubts. Example. I am taking some two loops beta here. Here it is x-axis, here it is y-axis, here it is z-axis. Okay. Here is a loop beta. Here is a loop beta. There are two loops here. Yes. So the current is flowing here. In this loop, the current is flowing like this. In this loop, the current is flowing like this. Clear? Yes. And this is having a radius. This is having a radius. How much is the current flowing here? I amperes. Here, how much is the current flowing? I amperes. This is having a radius A. This is having a radius A. And the distance from here to here is B. Clear beta? I want to find out what is the overall magnetic field intensity at point x is equal to B. I'll call this as a loop 1. I'll call this as a loop 2. What is the magnetic field at x is equal to B beta? Try to write this one. There are two current carrying conductors here, which are displaced at a distance B. What is the magnetic field at the try to write this one. I've changed the orientation here and I've changed the current directions here. One is at the center, other one is at a distance of B. Three things are involved here. So take care of those things and try to write down them. Okay. Yeah. Copy, right. Have you written that one? 2 times of original. Yes. Okay, see here, beta. Let us try to write down this one. At x is equal to B, what is the magnetic field? At x is equal to the overall magnetic field is magnetic field due to the first loop and as well as the magnetic field due to the second loop. Yes. So for the first loop, suppose if you want to find out the magnetic field here, for the first loop, you are at a distance of B. You are finding the magnetic field at a distance of B. And that too, if I put my fingers in the direction of current loop, my thumb in the direction of current loop, my fingers will going to show the direction of magnetic field. Direction of magnetic field is in the X direction. Yes. And you are at a distance of B. Observe carefully. So here it is. B total is equal to mu naught into I into X cap, I into A square into X cap divided by 2 into A square plus B square to the power of 3 by 2 plus you are finding here beta. For the loop 2, you are at the center. For the loop 1, you are at a distance of B. That is the reason why we have written the B here. Are you getting the logic? And one more thing here, what is the direction of the magnetic field? Here it is the current direction. If I put my thumb like this, my fingers will show the direction of magnetic field. Magnetic field is downwards beta. That is in the negative X direction. So here for the loop 2, you are at the center. If you are at the center, what is the magnetic field? Mu naught into I divided by 2 into A, which is minus X cap. Clear? Yes? Is it okay? Okay, you can, if you want, you can bring this one common. Mu naught into I divided by 2A. So here it is. X cap. A cube divided by A square plus B square to the power of 3 by 2 minus 1. Okay. Just for the clarity purpose, we have considered some example. Very good. Once again, B2. Nothing beta. For the loop 2, you are finding the magnetic field here. That means for the loop 1 at a distance, you are at a distance of B. For the loop 1, you are at a distance of B. And for the loop 2, you are at a distance of, you are at a center. So that is the reason why we use the center formula. That's all it is. But the current direction is like this. If I put my thumb like this, my fingers will going to show the direction of magnetic field. Clear? Yes. Let us have one question here. I'll going to turn the page. For a singleton loop of current, let me write down. For single turn loop of current, shown in the figure, determine B field at the center of the semicircular, at the center of the semicircular portion. At P. Here is a diagram provided in the question. Here is a diagram provided. That is the radius R, this is a point P, and the distance from here to here is 2R. Distance from here to here is R. This is a current flow direction. So the current carrying conductor is like this. It's bent like this. The current flowing is I. So he's asking what is the magnetic field at the center. The options are provided. Mu naught I by 4R 1 plus 2 root 2 by pi. Option B, mu naught I by 4R 1 plus root 2 by pi. Option C, mu naught I by 4R 1 plus 2 by pi. Option D, mu naught I by 4R 1 plus 1 by pi. Yes, what is the answer? Any answers from your side? Very good, Mr. Swain. Bhimalendu Swain. Yes, Vinita Chakka. Good. See here. Here is a current carrying conductor. It is twisted like this. Yes. So he is asking what is the magnetic field at the center beta. How do you find out the magnetic field at the center? The magnetic field at the center is due to this section, due to this section, due to this section, due to this section. Total due to the 4 sections. Okay, that is how you'll get the answer. But I want to do in only 2 sections. We can do this problem as a combination of 4 sections or combination of only 2 sections. Let me draw this diagram one more time. I'm going to turn the page. Here it is I amperes. I amperes. Here this is a point P. Here to here is R beta. This distance is 2R. So what I'll do, I'll just view this problem as a collection of 2 sections only. What is the collection of 2 sections? In the circular loop, half. In the square one, half. How it is like this. Here is a circular loop. Half in the circular loop. Yes, here is a point P. And what is the radius of this one is R. Plus half in the square loop beta. Square loop half side to R. So the overall side of this one is, here is a point P. What is the side of this one is 2R. What is the side of this one is 2R. So how you can see this problem beta? Combination of two sections in the circle, half of the circle, half of the square. Yes, let me turn the page here. What I mean to say here is the magnetic field at a point P is magnetic field due to circular loop by 2, magnetic field due to the square loop by 2. What is the magnetic field due to the circular loop? BC is equal to mu naught into I by 2A. S or not? What is the magnetic field at the center of the circular loop? Is mu naught into I divided by A. What is the radius we are having? R is the radius beta. Yes, so here it is 2 into R. What is the magnetic field due to the square loop? Square loop, what is the center? We have taken that as example number 2, and we have solved one numerical also. 2 root 2 I by pi d. If you remember, let me go back. What is the magnetic field at the center of the square loop beta with the side d? That is the second example. 2 root 2 I by pi d. That is for the H. You can also see from here 2 root 2 I by pi d. Clear beta? Yes. So here it is. Here it is mu naught into 2 root 2 I by pi d. So what is the side for the our question? The side is 2R beta. D is a side. So in our question, side is 2R. So here it is mu naught into 2 root 2 I by pi into 2R. Okay, fine. Now just substitute the values there. BP is equal to mu naught into I by 2R divided by 2 plus 2 root 2 into mu naught into I by 2 pi R divided by 2. BP is equal to mu naught into 4R mu naught into 2 root 2 I by 4 pi R. BP is equal to mu naught by 4 pi R common. 1 plus 2 root 2 by pi. So option A is the answer beta. Mu naught into I by 4R. 1 plus 2 root 2 by pi. Clear, beta? Let us have one more question. These are something very tricky questions. Let us have one more question. I'm going to turn the page. Something conventional type of question, but anyhow, the concept is important for us. I'll write down the question. An infinitely long straight wire carries 1000 amperes of current and in the vicinity there is a circle. There is a circular conducting loop of 100 mm diameter with the center of loop 1 meter away. 1 meter away from the straight conductor. Both the wire and loop are coplanar. Determine the magnitude and direction of current. Magnitude and direction of the current in the loop that produces a zero flux density at its center. Excuse. Yes, read the question carefully, beta. Any answers from your side? Little bit conventional type of question. Okay, anyhow. Any answers? No, not 0 ampere. Okay, let us try to understand the question first, beta. An infinitely long straight wire carries how much? Let me turn the page here. Always draw some rough diagram. From there, you'll get some idea. Okay. Here is a question. An infinitely long wire. Let me turn the page here. An infinitely long wire let me consider some coordinate system beta for my I'll consider some coordinate system for my convenience. Outside the board is x-axis, this is y-axis, this one is z-axis beta. I'll consider the current is upwards. In which direction I'm considering the current? See here, an infinitely long straight wire carries 1000 amperes of current in the vicinity of, and I'm considering here 1000 amperes above. Clear? In the vicinity of this one, there is a circular conducting loop of 100 mm radius beta. With the center of the loop 1 meter away from the straight conductor. So here, the center of the loop, what is the distance between these two things? What is the distance from here to here? 1 meter. Clear? And what is the radius of this one beta? The radius of this one is 100. Diameter is 100 mm. The radius will be 50 mm. Okay, fine. Let me go back. So what is the question here, beta? The question here is, determine the magnitude and the direction of current in the loop that produces a zero flux density at its center. Yes. So what should be the flux current in this loop so that the net flux density due to this loop and this due to this one will be zero at the its center. So we know that if I consider this current upwards, that he has not mentioned anyhow. I have considered the current in upward direction. So what would be the direction of magnetic field here, beta? Here it is like this. That means in this plane it is inside. So whatever the magnetic field, for the cancellation to happen, the magnetic field which is coming from the current carrying conductor is inside here, inside. So whatever the loop is generating, that magnetic field should be outside. For that to happen, the current should flow in the anti-clockwise direction. For that to happen, here the current should flow in the anti-clockwise direction. Here it is inside due to this conductor. And what about this one, beta? Due to this one, if I put my thumb like this, the magnetic field is outside. Outside is positive x direction. Here it is negative x direction. So there is a possibility for the cancellation there. So I'll call this current as a I. Clear? Yes. So we are using this notation, not R. For this one, we are using what is called a. Clear, beta? Yes. Observe carefully. Now let us proceed further here. I'll call this as a 1. This one as a 2. So I want to find out the magnetic field, net magnetic field here. Yes. So what is the net magnetic field there, beta? B total is equal to B1 plus B2. So what is this B total, beta? What is that B1? I'll call this is a I by mu naught into 10 to the power of 3 by 2 pi rho. Yes? Yes or not? Or let me write down the formula first. Mu naught into I by 2 pi rho into what is the current direction here? Inside. Inside means negative x direction. Plus, what is B2, beta? The current is flowing like this. The magnetic field is outside here. Outside means positive x direction. Yes. So here it is. Mu naught into I divided by 2 into A is positive x direction. So here it is B total is equal to mu naught into I. How much is the I? 10 to the power of 3. This must be equal to 0, isn't it? This we are represented with the I1 beta. Sorry. This is I1. I2 otherwise. This is I1 divided by 2 pi rho. What is the distance from here to here? Perpendicular distance is 1 meter. Minus x cap plus mu naught into I2 divided by 2 into A. What is the radius, beta? 50 mm, isn't it? 100 mm is a diameter. So the 50 mm is a, here it is 50 mm. 50 into 10 to the power of minus 3 into x cap is equal to 0. So which is equal to mu naught into I2 divided by 100 into 10 to the power of minus 3, which is equal to mu naught into 10 to the power of 3 divided by 2 pi. So I2 is equal to 100 into 10 to the power of minus 3 into 10 to the power of 3 divided by 2 pi. So finally, what is, I'm going to turn the page here. I2 is equal to how much, beta? I2 is equal to 50 by pi amperes. Okay. So if the I1 is upwards, the current in the loop must be anti-clockwise. If the I2 is downwards, current in the loop must be clockwise. That is observation. Yes. If I1 is upwards, then in loop, current is anti-clockwise. If or otherwise, if I1 is upwards, I2 is anti-clockwise. If I1 is downwards, then I2 is clockwise. So that is the thing. That is the magnitude of the current in the loop. Fine. This is a conceptual question. Fine. Let us take one more formula beta. I'm going to turn the page here. So how many formulas we have seen? Magnetic field due to the finite length conductor, infinite length conductor, magnetic field due to the conical, and magnetic field due to the circular loop. Now we're going to have magnetic field due to the infinite sheet. What it is beta? Magnetic field due to the infinite sheet. Have a look over this. It is a very simple formula. Magnetic field due to the infinite sheet. Magnetic field due to infinite sheet current beta. Sheet current will represent it with what? Symbol K. Its units are ampere per meter. That justification I've already given. Yes. No one should say ampere per meter square. It is an infinite sheet beta. So here the current carrying conductors are arranged on the sheet like this. It is a sheet like this. The current is flowing like this. If the current is flowing like this, what would be the direction of magnetic field? Magnetic field will circle around this one, isn't it? I need to put my thumb in the direction of current flow. My fingers will going to show the direction of magnetic field. That we already know. Yes. So the magnetic field would be like this, around this one. Yes. But this diagram is not correct. Why? Because I have drawn the only finite sheet. I'm talking about what is called an infinite sheet. That means it will extend up to positive infinite here. It will extend up to negative infinite here. It will going to extend up to positive infinite here. It will going to extend up to negative infinite here. Yes. So if I put my thumb in the direction of current flow, my fingers will going to show the direction of magnetic field. So what is the magnetic field direction beta? Like this. Clear? Yes. Now observe here, this is a finite sheet beta. Okay. I want to draw this view. I want to draw this view. Okay. If I see the sheet from this side, what I'll going to see? I'll going to see only the line. Yes. So this is a sheet. This is a sheet. If I see it from here, it will going to look like a line where the current is coming outside. And how I am characterizing this current? I am characterizing this current as a K. Units are ampere per meter. Okay. Now observe here carefully. I'll going to draw that view. That means this one. Here it is minus infinite to plus infinite. It is the infinite sheet. Okay. Current is coming outside beta here because I'm looking at this view. Yes. So the current is coming outside. How I am characterizing this current? I am characterizing this current as K. Units are ampere per meter. How the magnetic field is? Suppose if you consider the finite length, this will be like this, around this one. But it is the infinite extent. It will never encounter any bend in the sheets. No, it will never encounter any bend there. So the electric field, magnetic field, you will find everywhere. Tangential on both sides, isn't it? So this figure is not correct because this is only true for the finite sheet. Infinite sheet will never encounter these corners. These bendings are not observed. Clear? So how the magnetic field will going to look for the infinite sheet? Tangential, above one line, below one line. Tangential on both sides. It will going to bend at the corners, but as it is the infinite extent, it will never encounter any bends, any corners and any bends. So how does the magnetic field will be better? Like this. Here it is like this. So it will never encounter any bend, corners and bend. So here it is like this. H units are ampere per meter. Here it is. H units are ampere per meter. Clear beta? Yes. So for the infinite sheet current, the magnetic field is tangential on both sides. Okay. And how do you decide the magnetic? Let me turn the page here beta. How do you find out the magnetic field? You need to go make a use of this expression. B is equal to surface integral of mu by 4 pi into surface integral of K into dA cross R cap by R magnitude square. I'm not going to do any derivation here, which is not required for us. Formula is important beta. So what is this B? B after integration and all that story. B is equal to mu into K cross N cap by 2. Yes, this is a formula. What is this B? B is equal to mu into K cross N cap by 2. Units are Weber per meter square. So what is this B vector? Magnitude of the B vector? Magnitude of the B vector is equal to mu into K by 2. Why there is a cross product here? Why? Because it is a current direction cross unit vector. What is actually the magnitude is mu K by 2 is the magnitude of the magnetic field intensity. Yes. So you have to, if you want to find out the magnetic field direction, the current is coming outside, you need to take the normal here. What is that N cap is a normal. You can take this as a plus or minus N cap. This will become minus or plus n cap. Take the cross product of these two. Current direction is outside. Current direction cross unit vector is a HT2, HT. Yes. So what this is giving is just it's the direction, cross product. Fine. And similarly, you can find out the H vector. What is the H vector, beta? H vector is equal to K cross N cap by 2. Units are ampere per meter. So the H vector is equal to K by 2. Clear? Yes. Fine. Okay. Let us take one question here. It is a very simple formula, beta. Let me take one simple question here. A plane y is equal to 0 carries a uniform current density. Uniform current density 30 Z cap milliampere per meter at 10, 20, -2. What is the magnetic field intensity? Options are given. -15 X cap milliampere per meter. Option B 15 X cap milliampere per meter. Option C 18.85 X cap milliampere per meter. Option D 25 X cap milliampere per meter. Yes. There is no practical example for sheet current. It is the infinite sheet. You can take the capacitor plates. That is also not exact example for the infinite sheet current. All these are yes, beta. Let us have some rough diagram so that you'll understand what we want trying to do here. Clear? Yes. So here is a thing like this. Here is a infinite sheet beta. Where this is infinite sheet current is located at y is equal to 0 plane. That means it is in the xz plane. Let me take the things accordingly. Here it is x-axis beta, here it is y-axis, here it is z-axis. Where this infinite sheet current is placed in the y is equal to 0 plane. That means it is in the xz plane, something like this. So the current is flowing in which direction, beta? Z direction. Yes. So here is a Z direction like this. Clear? Yes. So if the current is flowing like this, what is the direction of magnetic field? The magnetic field is tangential on both sides. Suppose if you take the point above this one, the magnetic field is like this, below this one like this. Below it is like this. H units are ampere per meter. Here it is. H units are ampere per meter. So if the point is above the sheet, the magnetic field is in the negative x direction. If my point is below the sheet, the magnetic field is in the positive x direction. Yes. So where this point is beta? 1, 20, -2. Is it above the sheet or below the sheet? It is above the sheet, isn't it? If it is above the sheet, why it is above the sheet? The infinite sheet is placed at y is equal to 0. But this point is at y is equal to 20. It is above the sheet. As it is above the sheet, so the magnetic field direction is in the negative x direction. Directly you can decide the answer like this. -15 is the answer. Okay, or otherwise you can go by the formula. What is the formula I have given? And what is the current here, beta? K. K is equal to 30 Z cap. And what is the normal to this one, beta? Normal to this one is Y cap. Below beta, what is the normal to this one? Minus Y cap. Clear? Let me turn the page here. What is the formula given? H is equal to K by 2 cross N cap. What is this K beta? 30 Z cap. Cross N cap. What is the normal to the sheet? Plus or minus Y cap. Z cap cross plus or minus Y cap. He is asking at what point at 1, 20, -2. Is above the sheet or below the sheet? Here the y infinite sheet is placed at y is equal to 0. So y is equal to 20 here. It is above the sheet. If it is above the sheet, what is the normal direction, beta? Normal direction is in the positive y. Clear? So what happens to this one? Here it is. H is equal to 15 into Z cap cross Y cap. What is this Z cross Y, beta? Here it is. -15 X cap. Milliampere per meter. Is the answer. Yes, what is the answer here? Option A is the answer. But let me do add some more points. Anyhow, we have got answer. So at 20, -20, 20, what happens? -20, -20. What happens, beta? -20, -20. This point will be below the sheet, beta. If I am below the sheet, 20, -20, -20, 20 comma minus 20 comma 20 is below the sheet. If I am below the sheet, what is the normal? Is minus y cap. Yes. So what happens to the magnetic field? H is equal to 15 into z cap cross product with minus y cap. So H is equal to z cross y is minus x. So one more minus is there, it will become plus. Milliampere per meter. Let us take one more point. It's a very simple formula, beta. 10 comma 10 comma 10. 10 comma 0 10 comma 10 comma 10. It is above the sheet. If I am above the sheet, the magnetic field is H is equal to 15 z cap cross y cap. So the H is equal to minus 15 x cap milliampere per meter is the answer. Clear? Yes. Okay, beta. Fine. So these are the some of the formulas which you need to remember. Questions are noticed from these formulas, beta. Fine. Okay. You need to solve more number of questions. Some of the models have solved in the classroom. And you need to collect the more number of questions and you need to solve them. Clear? Let us go to the new concept here. Yes. At 0, 0, 0, it is not defined. One of your friend is asking, what happens at 0, 0, 0? On the sheet, it is not defined. Isn't it? Magnetic field is not defined on the conductor. Charge is not, electric field is not defined on the charge. Isn't it? See, for example, if you have a charge Q, what is the electric field? E is equal to Q by 4 pi epsilon R square. If I make R is equal to 0, it tends to infinite. That is that mean electric field is infinite at on the charge? No, it is not defined. The electric field is defined just after the charge. The electric field is a energy format which exists around the charge, not on the charge. Yes. Similarly, current also. If you have a current carrying conductor, what is the magnetic field, beta? B is equal to mu I by 2 pi rho. If I take rho is equal to 0, it tends to infinite. No, magnetic field exists around the current carrying conductor, not on the current carrying conductor. It is not defined. It is not present there. So just after the current carrying conductor, it will exist. Then one can ask why, sir? That is the property of the electric field and magnetic field. If I take x is equal to negative sign, then what happens? Remember, I have drawn only in the positive xz plane. You must remember that it is an infinite sheet. It is like this actually. The correct exact diagram is like this. Just to make the thing simple, I have drawn like that. But you must remember that it is an infinite sheet, beta. It is extending from here, it is positive infinite. Here it is negative infinite. Here it is positive infinite. Here it is negative infinite. That is all the stories. What you don't know, beam length. It is an infinite sheet. Okay, fine. We'll go to the new concept, beta, here. I'll going to turn the page. Okay, beta, see here. I'm going to introduce some new vector, what is called a magnetic vector potential. We are heading towards the one more Maxwell equation. So here it is, magnetic vector potential. Magnetic vector potential. It is represented with the A. Units are Weber per meter square. Yes. Now let us consider here. Consider expression for the magnetic field beta. What is expression for the magnetic field? B is equal to mu by 4 pi into volume integral of S J into dV cross R cap by R magnitude square. How that unit vector can be written, beta? How this unit vector can be written? Vector by its magnitude. That means this will become B is equal to mu by 4 pi volume integral of J into dV into vector by its magnitude cube. Clear? Yes. Now observe carefully here. Here there is a cross product beta here. There is a cross product inside the integration. What it is? There is a cross product inside the integration. There is a cross product inside the integral. We have not done any derivations of this one. A derivations of finding the magnetic field, so that you would have understood what is the difficulty involved in using these equations. What I'm saying here is there is a cross product. There is a cross product is present inside the integration. So because of this one, what happens? The mathematics is very lengthy. So what I want to do, I want to bring this one outside beta. I want to bring that cross product outside. I'll repeat again. So the cross product is there inside the integration. So the mathematics is very complicated. So I want to bring that cross product outside the integration. So I'm going to make a use of one property here from what is called a vector calculus. There is one property from vector calculus. From the vector calculus, there is a property. What is that property? Vector by its magnitude cube is equal to minus gradient of 1 by r beta. So here, vector by its magnitude cube. Vector by its magnitude cube is equal to minus gradient of 1 by r. I'm going to substitute this one there. Clear? Yes. Yes. So what I'll do here, I'll just bring this one here and I'll substitute here. I'll going to substitute that property there. So what it is? B is equal to mu by 4 pi volume integral of J into dV cross product with minus gradient of 1 by r. So the vector product is not, this cross product is not commutative. What I mean to say here is, F1 cross F2 is equal to minus F2 cross F1. So with this knowledge, what I can do, I can interchange the positions of J and del. I'll write this one here and this one there. So I can, that minus sign will disappear. Okay. So what happens to this B beta? B is equal to mu by 4 pi volume integral of del cross J into dV by R. What is happening here is, this is operating on the source beta. This is at the source point. And where is this del? Del is operating at the field point. Where it is operating? This is operating at the field point. Source point and field point. Let me turn the page here. What I mean to say, I'm going to show with the help of diagram. For example, here is a current carrying conductor. How much is the current flowing through this one? J and dV. And here I want to find out the magnetic field somewhere here. The magnetic field is inside. And the distance from here to here is R beta. Here is the source point. So this integration is acting on the source point. Yes. So here it is acting. Here it is acting. This del is acting on the field, this location. So what I mean to say here is, field point is here, source point is here. So the order of operation doesn't matter. So if you operate this one, and after that this one, doesn't matter. Or if you operate this, and then this, doesn't matter. So the order of operation doesn't matter. The source is here, field point is here. So they are nothing to do with each other. Here is a source point. And here is a field point. Clear? So with this argument, what I'm going to do, let me go back. I'm going to bring this del outside. Clear, beta? Yes. So here it is. B is equal to mu by 4 pi del cross into volume integral of J into dV by R. You can bring this to mu by 4 pi epsilon inside. Del cross mu by 4 pi volume integral of J into dV by R. So successfully, just forget about all that story, what we have done here, what are the arguments I have given, everything, just forget about this one. Mathematics is not required for us. So what is happening here? There is a cross product inside. I have brought that one outside. Yes. So if I bring that one outside, it will become this del cross. Yes. Successfully, I brought this cross product outside. Now it is a del cross. Yes. So you have got some new vector here. In that vector, you don't have any cross product. That vector is called magnetic vector potential. And one more thing here, what is this B beta? B is equal to del cross A. Yes. And what are the units for this one? Its units are Weber per meter square. What are these units, beta? Dou by dou x, dou by dou y, dou by dou z, isn't it? Its units are per meter. So obviously these units will become Weber per meter. In one of your previous paper, this was a question, but you do not find such a silly questions nowadays in the GATE exam. In the engineering service, these kind of questions are expected. One question will be there from the units. One question will be there from the identifying the equations. Or he may ask you to identify the relation between B and A. Yes, or he may ask you to identify. One question will be based on the units. One question will be based on the identification of equations. Yes, so surely there will be one question from the identification of equations. You can guess the engineering service paper pattern. If you do some research, if you do some survey, for every topics, you can guess around some from each and every subject, you can guess some topics. Regularly, there will be a questions from that. But in the GATE exam, you cannot guess. There can be from any question, from any corner of your subject. Clear? Let me turn the page here. So the units for this A is Weber per meter. Now, let us try to find out this A. Here is the A expression, beta. Mu by 4 pi volume integral of J into dV by R. Now, I want to write down that one for the different currents. What is the current element we have already given? If you remember, current element. What is the current element, beta? I into dl is equal to K into dA is equal to J into dV, if you remember. Here it is ampere meter, ampere per meter, meter square, ampere per meter square, meter cube. Okay, fine. So what happens to the A? A is equal to mu by 4 pi. For the volume current is J into dV by R. This is for what current, beta? Volume current. It is represented with the J. Units are ampere per meter square. And A is equal to, for the surface current, you need to perform surface integral. A is equal to mu by 4 pi surface integral of K into dA by R. This is for the sheet current. It is represented by the K. Units are ampere per meter. Here it is mu by 4 pi. Line integral of I into dl by R, beta. This is for the line current. Here it is I. Units are ampere, not ampere per meter. Yes. So once you are getting A, and then if you want to find out the B, what you need to do? B is equal to del cross A. Clear, beta? Okay. So why we are introducing? So what you need to remember for your exam? The relation between B and A and different expressions for the A. for the different types of current, volume current, sheet current, and line current. Okay. So does this magnetic vector potential have any meaning? No. It has got no physical significance, but it is defined to make the analysis simple in the evaluation of magnetic field due to the various current distributions. That's all it is. It is only for the mathematical simplification, but it has got no physical significance. Yes, let me write down that point here. From here, we're going to get some other conclusions that we're going to do anyhow after the break. But before break, let me write down one note here. Let me turn the page here. The magnetic vector potential, what it is, beta? The magnetic vector potential A Weber per meter has no physical significance, but it is defined to make mathematics simple in the evaluation of magnetic field due to various current distributions. Okay, beta. We'll continue. We'll take 20 minutes break. After that, we need to develop some more theory. We'll continue after the break. Electrostatic potential has a significance. It is the work done by the unit charge. Actually, it is a historical reason. Suppose if you develop one vector from the others, if you find out the one field from the other field, E is equal to minus gradient of V, and then B is equal to del cross A. So the E is developed from the gradient of V. So this is called potential. B is developed from curl of A. So this is called potential. With that reference, it is called potential, but it has got no meaning. If something is developed from other thing, that the other thing is called potential. Okay, we'll continue after the break, beta. 20 minutes break. Welcome back, friends. So here it is a magnetic vector potential beta. Magnetic vector potential has no physical significance, but it is defined to make the mathematics simple in the evaluation of magnetic field due to the various current distributions. So what can be expected in our exams is based on identification of equations. You should know the expression of A for volume current, A for sheet current, and A for line current. Once you know the expression for A, you can find out the B. B is equal to del cross A beta. Clear? I'm going to turn the page here. Now observe here carefully. Let us do some more analysis beta here. Now let us consider this equation. B is equal to del cross A. Let us proceed further. Let me discuss some more theory. Consider B is equal to del cross A. Now what I will do, I'll apply the divergence on both sides. If I apply the divergence on both sides, what happens? Divergence of B is equal to divergence of del cross A. What is this divergence of curl of vector beta? Divergence of a curl of a vector is nothing but 0, isn't it? So what happens to this one? You will going to get divergence of B is equal to 0. Array, very interesting thing. If you compare this one with the electrostatics, what we had in the electrostatics? Divergence of D is equal to rho V. This is a Gauss law, isn't it? In the differential form or point form. Here it is a Gauss law in the point form or differential form. Gauss law for magnetic field beta. This is for the electric field, isn't it? That is under the context of electrostatics. Here it is under the context of magnetostatics. So here it is called Gauss law in Gauss law for magnetic field. In a differential form. From the divergence theorem, what can be written? From divergence theorem. What is the divergence theorem? Closed surface integral of B dot dA is equal to volume integral of divergence of B into dV. But what is this divergence of B beta? Is equal to 0. So here you will going to get 0. That means closed surface integral of B dA is equal to 0 beta. But what you have learnt in the electrostatics is, let me write down that one also here, is this one. Closed surface integral of dDA is equal to charge ENC, enclosed. Yes or not? Array, So this is called what? It is looking something similar. This is called what? Gauss law for magnetic field in the integral form. What is this one? Gauss law for magnetic field in integral form. Clear? Yes. Let us try to have some interpretation of this one. Let us try to have some interpretation of these equations, beta. We know the interpretation of this equation. What is the interpretation of these equations? Net electric flux coming out is equal to, what is this one, beta? Net electric flux coming out of any closed surface is equal to charge inside that. What is this one? Net flux coming out of the small piece of a box is equal to charge inside that. Charge inside that is the volume charge, beta. Yes. So you can extend the same concept here. So the net magnetic flux coming out of any closed surface is equal to charge enclosed by that one. That means net charge in the system is 0. Here also, if you consider the small box, the net charge in the system is 0 in the case of magnetostatics. Why like that? Let me explain with the help of some examples, which are very interesting. I'll going to turn the page. So here is a case, beta. For example, I'll going to draw some 3 figures here. Let us consider a circular loop, current loop. Here is a current loop, beta. If I put my thumb like this, my fingers will going to show the direction of magnetic field. Actually, the complete direction of the magnetic field looks like this. Complete direction of the magnetic field looks like this. Just a minute. Yes, beta. So if this is the case, if the current is flowing like this, what would be the direction of magnetic field like this? Actually, the total diagram for the magnetic field is like this. Where we have calculated is somewhere here. Somewhere here, the magnetic field is like this. Clear? Yes. Fine. But in general, it is how it looks. So what is this one? It is the magnetic field due to the current loop. Clear? Yes. Similarly, if you consider a permanent magnet beta, what is the permanent magnet looks like? Or you can also say bar magnet. Here it is north pole, here it is south pole. So here the a magnetic field is like this from the north to the south. This is for what? Bar magnet. Or you can say permanent magnet. Clear? Yes. Suppose if you consider the dipole charge beta. Positive charge here, north pole I can call. Here it is a negative charge, here I can call it as a south pole. This is for what? Dipole charge beta. That means the nature of the magnetic field around the current loop, the nature of the observe the nature of the magnetic field. It is like this. Here also like this. Here also like this. So the nature of the magnetic field around the current loop and bar magnet and the dipole charge are same. So that means the nature of the magnetic field, this is equivalent to this one. This is equivalent to this one. That means whatever you can apply here can be applied here, can be applied here, and vice versa. Interesting. So let me consider the small piece of a box here beta. So the number of lines entering and leaving are same. That means the net magnetic flux is 0. But that is not the case in the case of electrostatics. Let me turn the page here. What you can have in the case of electrostatics, for example, in electrostatics, in the case of electrostatics, you can have like this. You can have 4 microcoulombs. You can have minus 1 microcoulomb. If it let us say this 4 microcoulomb is creating the 400 lines and minus 1 microcoulomb is taking the 100 lines, how many net lines will be there? Net charge in the system is 3 microcoulombs. But here there is nothing like that. There is nothing like that such scenario. Always if there is a positive charge, there will be a negative charge. North pole, south pole. You can notice the nature of the magnetic field here. So then for the magnetostatics case, the net charge in the system is 0. Okay. So if you consider the small piece of a box or any arbitrary closed surface, number of lines entering and leaving are same. So the net magnetic flux is 0 beta. Clear? Yes. So what is the interpretation of this for these equations? The net magnetic flux is 0. Or the source for the magnetic charge, magnetic field is a dipole charge. Whatever how small you consider, in that you will find the north pole and south pole. Yes. So that is called, let me write down. Gauss law for magnetic field. B Weber per meter square. What is this Gauss law for magnetic field is saying? The net magnetic flux coming out of any closed surface is always zero. Why? Because the net charge for the magnetostatics is always zero. You cannot have 1 microcoulomb of charge separately, one north pole separately, or one south pole separately, isn't it? It is something like a buy one get one free offer. Okay, beta? Yes. Fine. So let me write down that statement here. The net magnetic flux coming out of any closed surface is always zero. That is magnetic flux net is equal to zero. Okay, fine. This is a definition form. This is a definition form, beta. For every law, we are defining the three forms, isn't it? One is the definition form. This is a different integral form, and this is a differential form. Clear? Fine. Now observe here carefully. So what is this interpretation, beta? What is this divergence of B is equal to zero is indicating? Non-existence of magnetic monopoles. You cannot have a north pole separately or south pole separately. It is something like a buy one get one free offer. Okay, so the magnetic charges always exist like a dipoles. This was one of your theoretical question. So the equation divergence of B is equal to zero indicates non-existence of magnetic monopoles. That is magnetic charges always exists as dipoles. Clear, beta? Yes. Fine. There are some integrals which you need to remember. Let me turn the page before going to the numericals. There is some integrals which you need to remember. Note. First integral is like this, beta. Line integral of EDL. What is this is? Second one is surface integral of DDA. Third one is line integral of HDL. Fourth one is surface integral of BDA. What is the first integral, beta? What is the first integral? I want answers from your side. First integral is a voltage or EMF, you can say. Very good. Okay. Here it is a EMF or voltage, you can call. What is the second integral, beta? What is the second integral? Come on, I want answers from your side. What is the second integral? It is not a charge, it's just a flux. It is just a flux. It is a, what is called electric flux, Psi. It is not the charge, beta. See here, if this is a closed, then it is a net flux, which is equal to charge. But here just it is the integral, beta. Clear? Yes, it's just the electric flux. So with the same theory, this is MMF, beta. And this is a magnetic flux, Psi m. What are the units for this one? The units for this one is volt per meter multiplied with the meter. So here it is volt. Here it is coulomb per meter square multiplied with the meter square. Here it is a coulomb. Here it is ampere per meter multiplied with the meter. Here it is ampere. Here it is Weber per meter square multiplied with the meter square is Weber. If this is closed, then it is, what happens we'll discuss later. If it is this is closed, for the electrostatic case it is 0. That is a conservative property which we have already seen. If this is closed, then it is a net electric flux which is equal to charge enclosed. That is Gauss law. If this is closed, what happens? That we're going to see in the Ampere's law. If this is closed, what happens, beta? That equals to net magnetic flux which is equal to 0. That we also have seen. Clear? Yes. These are just integrals, beta. These are just integrals. Fine. Okay. If these are closed, then it is a conservative property. If this is closed, this is a Gauss law. If it is closed, Ampere's law, this is Gauss law for magnetic field. But these are just integrals. Fine. So let us, with this backup, let us try to solve some questions. I'll going to turn the page. Here is a question. Given magnetic vector potential, given a magnetic vector potential, A is equal to minus rho square by 4 Z cap Weber per meter. Calculate the total magnetic flux crossing the surface calculate the total magnetic flux crossing the surface. Phi is equal to pi by 2 comma rho is ranging from 1 to 2 meters. comma, phi is ranging from 0 to 5 meters. Yes, beta. Here is a question. So the given magnetic vector potential A is equal to this one, beta. A is equal to minus rho square by 4 z cap Weber per meter square. Calculate the total flux crossing the surface. Phi is equal to pi by 2. Rho is ranging from 1 to 2. Pi is from 0 to 5. Clear? Observe here carefully. Here is a solution. First, find out the flux density beta. B is equal to, we know that del cross A. Then you can find out what is called a magnetic flux. Yes, by performing what is called a surface integral. Clear? Yes. Let me write down here. You need to find out del cross A. Find which coordinate system is this? Cylindrical coordinate system. What is the del cross A in the cylindrical coordinate system? 1 by rho into rho cap into rho into phi cap into z cap. Dou by dou rho, dou by dou phi, dou by dou z. Here it is A rho. A rho, rho into A phi. Here it is AZ, which is equal to 1 by rho into rho cap, rho into phi cap, z cap. Dou by dou rho, dou by dou phi, dou by dou z. A rho is 0. A phi is also 0. This one is minus rho square by 4. So what is this one? B is equal to 1 by rho into rho cap into this minus this into this. That is rho cap into 0 minus 0 minus rho into phi cap into this into this minus this into this, which is minus 2 rho divided by 4 minus 0 plus z cap into this into this minus this into this, 0 minus 0. So here it is phi cap into rho into phi cap into minus 2 rho by 4 minus 0 plus z cap into 0 minus 0. Clear beta? So what happens to this one? Here it is 1 by rho into rho square by 2 into phi cap. Let me turn the page here. So the B is equal to rho by 2 phi cap. Is that correct? Yes. Units are Weber per meter square beta. So once if you have got flux density, you want to find out what is called a flux. What is the flux psi m? Psi m is equal to surface integral of B dot dA. And what are the limits here? limits are rho is ranging from phi is fixed, rho is ranging from 1 to 2. Z is from 0 to 5. Phi is from pi by 2. Phi is only 5 by 2. Clear, beta? So it is phi is equal to fixed, beta. It is rho z plane. So here it is rho phi z. Scaling factors are 1 rho 1. Here it is dA is equal to multiplication of first two rho d rho d phi z cap. Multiplication of next two rho d phi dz rho cap. Last two dz d rho phi cap. Here phi is equal to constant beta. So what about this d phi? D phi is equal to 0. That means first two terms are 0. So what is this dA? dA is equal to dz d rho phi cap. So psi m is equal to surface integral of B. What is the B beta? Rho by 2 into phi cap. Dot product with dz d rho phi cap. Clear? Yes. So what happens to this one? Here it is surface integral of rho by 2 into rho into d rho into dz beta. Separate out the variables. Take 1 by 2 outside. Here it is rho d rho. Here it is dz. 1 by 2 into rho square by 2. Rho limits are from 1 to 2 beta. Here it is z. Z limits are from 0 to 5 beta. Upper limit minus lower limit. 1 by 4. 4 minus 1 into 5. 15 by 4 beta. So the magnetic flux is equal to 3.75 Webers is the answer. <clears throat> 3.75. Very good. Good. Now what I'll do here, I'll change the limits here. Repeat the previous question for the following limits. I'm going to turn the page. Question here is, repeat the previous question for following limits. What are the limits here? The phi is ranging from 0 to pi by 2 and rho is ranging from 1 to 2 meters and z is ranging from 0 to 5 meters. Yes, what is the answer? If these are the limits. I want answers from your side. Come on, speak out. Same, no? Just think about it. What is the difference between the previous limits and these limits? Previous question is this one. These are the limits. Phi is equal to constant. It is not ranging. Here phi is ranging. 0. Very good, beta. Here two coordinates are changing. It is a surface or it is a plane. It is a surface, isn't it? But here in this question, here three coordinates are changing. It will going to indicate the closed surface. Yes. So what is asking? Is asking us to find out what is called a net magnetic flux. Is asking us to find out the closed surface integral. That is nothing but a net magnetic flux. Net magnetic flux is equal to closed surface integral of P dot dA. So what is the net magnetic flux, beta? 0. 0 is the answer. Clear? Let us take one more question. The line integral of vector potential A around the boundary of a surface S represents which one of the following? Flux through the surface S. Option B. Flux density in the surface S. Option C. Magnetic field intensity. Option D. Current density. Yes, what is the answer, beta? See here, beta. Line integral of vector potential A around the boundary of the surface S represents the which one of the following? Here is the surface S. Surface will have what kind of boundary, beta? Surface will have a closed boundary. Yes or not? Surface will have, this surface is having a what kind of boundary? It is having a closed boundary. So indirectly it's asking us to find out what is called closed line integral. This is a surface. This surface is having a closed boundary. So it's asking us to find out what is called closed line integral, indirectly or directly. So what is this closed line integral, beta, of ADL? From the Stokes theorem, you can apply surface integral of, let me write down here. So the integral here is closed line integral of ADL, which is equal to surface integral of del cross A dot ds or dA, beta. What is this del cross A? Is nothing but a flux density. Yes. So here it is surface integral of B dot dA or ds. This is nothing but a magnetic flux psi m. Units are Webers. So what it is indicating? It is indicating the flux through the surfaces. It is a magnetic flux through the surfaces. So option A is answer. Very good. Some of your friends have answered. So what is the more appropriate wording here? Magnetic flux through the surfaces. Let us take one more question, beta. If vector B is equal to x square x cap minus xy y cap minus kxz z cap represents the magnetic field. The value of the constant K must be 0, option B 2, option C 1, option D 3. Yes. What is the answer, beta? Yes, what is the answer? If it is a magnetic flux density, yes, very good. If it is a magnetic flux density, its divergence must be 0. That's all it is. Okay, beta, see here. So divergence of B is equal to 0. So it is dou by dou x of x square plus dou by dou y of minus xy plus dou by dou z of minus k xz is equal to 0. So here it is 2x minus x minus kx is equal to 0. X minus kx is equal to 0. X is equal to 1 minus k is equal to 0. So from here, k is equal to 1. Okay, these are the some of the numericals on the concepts what we have learned so far. Let me turn the page here. We'll go to the new concept. What is called Ampere's law? Yes, or it is also called Ampere's circuital law. Let us see how much we can do in the today's session, and the rest of the things we'll discuss in the next session. Ampere's law, beta. Or Ampere's circuital law. What it is? The EMF induced in the loop. Sorry, I'm extremely sorry. The line integral of magnetic field intensity. Let me write down the law here. The line integral of magnetic field intensity, which is also called MMF, around the closed loop is equal to total current enclosed by that loop. The line integral of magnetic field intensity around the closed loop is equal to total current enclosed by that loop. That is MMF in the loop is equal to I enclosed ENC. Yes. Okay. MMF in the loop is equal to I enclosed, beta. Now let me explain this one. What does that mean? Now let us consider the current carrying conductor. Here is a current carrying conductor. Here current is flowing. How much is the current? I amperes. If the current is flowing like this, there will be a magnetic field around it. Just for the magnetic field around this one, just for the representation purpose, I will going to show with the arrow. Don't think that magnetic field is present only here. Magnetic field is present around this one. Just symbolically, I am representing there. Now let us consider the different loops here. Here it is the loop 1. Here it is the loop 2. And here it is the loop 3. And here it is the loop 4. So what is this loop 1, loop 2, loop 3? They are enclosing the current carrying conductor. And loop 4 is not enclosing any current carrying conductor. And one more point, beta, the current can't flow simply in the wire which is kept in the air like that. It is understood that it is connected to the source. That I am not showing. Okay, so what is this Ampere's law? The line integral of magnetic field intensity around the closed loop is equal to total current enclosed by that loop. That means that is closed line integral of HDL is equal to IENC, enclosed. Clear, beta? Yes. Now let me turn the page here. So what is the MMF in the loop 1 according to the law? I'm going to explain here with the example. Just this is the example, beta. What is the MMF in the loop 1, beta? MMF in the loop 1, this can be written as closed line integral of HDL loop 1, which is equal to I enclosed. What is the current enclosed is the I. That's all it is. Yes, let me go back. Loop 2 is also I, loop 3 is also I, but loop 4 is 0. That's all it is. So what is the MMF in the loop 2? H dot DL, which is equal to I ENC, which is also equal to I. You no need to perform the closed line integral. Directly you will get it like this. Then what is the MMF in the loop 3? L3 HDL is equal to IENC, which is equal to I again. Then MMF in the loop 4 is closed line integral of L4 HDL. Here also IENC, enclosed. So the current enclosed for the loop 4 is 0, beta. Okay. Let us take, to appreciate this concept, let us take some numericals here. Interesting, simple. Previously asked. Find MMF in the following loops. Number 1. Here is a loop beta like this. Here it is a loop direction. And this is enclosing, let us say, 3 current carrying conductors. Here it is, current is going inside 2 amperes, going inside 4 amperes, coming outside 1 ampere. So what is the MMF in the loop here? Come on, speak out. Yes, beta, what is the answer? 5 amperes. Positive 5 amperes or negative 5 amperes? What is the need? What the reference need to be taken here? See here, observe here carefully, simple things. You need to consider only the current enclosed beta. See here, the current here 2 amperes is going inside, 4 amperes inside, 1 ampere outside. So if it is inside, what is the direction of magnetic field? Its corresponding magnetic field like this. Here it is like this. Here it is like this. So if the magnetic field associated with the current carrying conductor and the loop directions are same, consider that corresponding current as a positive current, otherwise negative current. Clear? So what is the MMF in the loop beta? MMF in the loop, which is also called closed line integral of HDL, which is equal to I ENC, which is equal to 2 amperes plus 4 amperes minus 1 ampere. So which is 5 ampere is the answer. Okay, beta. Let me turn the page here. Let us take one more question. Here is the thing. This is a loop direction beta. Minus 1 ampere, 2 amperes, 1 ampere, 10 amperes. What is the answer? Yes. Story remains the same, beta. Nothing new here. You consider its corresponding magnetic field. Here current is going inside. So the magnetic field would be like this. Here it is like this. Anti-clockwise. Here it is clockwise. But you need to discard the current. Anyhow, here it is clockwise. You need to discard the current which is outside. Just you need to consider only enclosed currents. So what it is? MMF in the loop is equal to closed line integral of HDL, which is equal to IENC. So here it is, loop direction and magnetic field directions are same, beta. So consider that current to be +2. Here the loop direction and magnetic field directions are opposite, beta. So here it is minus of -1. Here the loop direction and magnetic field directions are opposite. So here it is minus of +1. So how much is this? 2 amperes is the answer. Clear? Yes. Let us take one more question. I'm going to turn the page here. Try to observe this one, how I am drawing this question, because visualization is important. Number 3. Visualization is important for this question. Here is the thing. There are 3 current carrying conductors here. Here it is 2 amperes. Here it is 2 amperes. Here it is 3 amperes. Here it is 4 amperes. Now there is a loop here, beta. This is a loop direction. Here is a loop direction like this. This is a loop direction. There is a single loop rotated like this. Yes, what is this was one of your previous question. What is the MMF in the loop? Yes. What is the MMF in the loop? Come on, speak out. Yes, beta. Any answers? Good. Very good. Yes. Simple thing. There is a loop here rotated like this. So what you will do, I'll just reverse the center one, center conductor. If you reverse the center conductor, you'll get a big loop, or no need of that one also. If the current is going up, what would be the direction of magnetic field, beta? Here is the magnetic field. Here is a magnetic field. Here is a magnetic field. So the magnetic field direction and loop directions are same. Clear? Yes. So what is the MMF in the loop here? MMF in the loop is equal to closed line integral of HDL, which is equal to IENC. So what is the I current enclosed is the same. The loop direction and magnetic field directions are same. So 2 plus 3 plus 4, which is equal to 9 amperes is the answer. Let us take one more question. That was also previously asked. Number 4. There is a current carrying conductor is like this, beta. How much current it is carrying? I current. There is a one more current carrying conductor. I amperes. Here it is I amperes. Here this is the thing. Yes, what should I do? Here the only one wire rotated 3 times. Options are given. 4I, option B, 3I, option C, 2I, option D, I. Come on. Come on, speak out. What is the answer? 4I is the answer, beta. So you can split this one into the total 4 loops. That's all it is. Call it as a 1, 2, 3, and then 4. So that is how you need to approach. What is the corresponding here? It is going inside, beta. So the magnetic field direction is like this. Here it is like this. Clear? So what is the MMF in the loop? Can be written as MMF in the loop 1 plus, according to the law, which is equal to closed line integral of HDL, which is equal to I ENC, which is MMF in the loop 1 plus MMF in the loop 2 plus MMF in the loop 3 plus MMF in the loop 4, beta. So what it is? Current enclosed is I plus I plus I plus one more I. So here it is. MMF in the loop is equal to 4I. Option C is the answer, beta. Sorry, option A is the answer. Okay. See here, this is a definition form. We need to define the integral forms and point forms, but I'll postpone to the next session. Now I'll open my session to the doubts clearing. Now the session is open for your doubts. Just raise your hands, I'll come to you. Mr. Swain.
Sir, once previously I got an idea that a magnetic monopole exists, means at some temperature is very less. Is there any possibility?
Yes, there are in the physics, there is an argument. In the physics, there is an argument that there is existence of magnetic monopole. But as far as our electromagnetic theory is concerned, this is enough.
Sir, in that question, in that loop, how we are choosing that loop means h dot dl for this is only single loop rotating many times.
That one, single loop. Yes.
But how it is means that single loop I enclosed is adding add.
Effectively, this is close. Look, it is a crossing for this one, isn't it? There is a crossing here. So if you treat this as something like a work done, integral from here to here and integral from here to here, path will be same, isn't it? If you think in terms of path or a distance.
I think the first time, sir, question it is difficult. This question is for I see for first time and it will be difficult. I feel difficult in that question. It's understanding of that loops.
This one,
this last question. Yes.
So here, EMF induced by the loop. Here you have to treat it as a loop. That is how it is. Actually, you need to cross check this one. You have to split this one as a four loops, because even though it is crossing, even though it is not touching, but it is effectively acts like a one loop.
Yes, sir.
That's all it is.
Like, can we say that when we are doing in the electrostat, that Gaussian surface, the cylindrical surface we are choosing, it is finite, but
Yes.
the length is infinite. Means we are not enclosing total current. Means total surface we are not including. We are some part we are enclosing that Gaussian surface, and we are calculating that flux.
No, what interpretation you are doing, I'm not getting.
Actually,
see if it is closed like this. Can you apply this Ampere's law? No.
No.
Even though it is crossing, you cannot treat that as a closed one.
But it is effectively that a cross one.
If it is a closed one, and if the crossing happens, then also you can split that one into the loops. That's the thing.
Thank you.
Any more questions? Yes, Vishnu.
So my same thing here, sir. How did we like? Usually, this entire definition is on the fact that we consider only one loop, no, sir. Yes.
Not one loop. Enclosed loop.
One enclosed loop. Sir.
Enclosed current by the loop.
I mean, so my doubt is the last problem only, sir. Like other problems, I understood it the fact that we are only considering one loop. So we are only writing this current one time. When we are considering multiple loops, the same current, then why are we considering 4 currents, sir? That itself.
Enclosed. This is enclosing. Here to here, there is a one enclosure.
Okay, sir.
This here to here, there is a one more time enclosing.
Okay.
Here to here, it is one more time enclosing. That's how it is. That's how the law is. And if you want to verify that one, you need to find out the line. You have to take some loop and you need to integrate that one like that.
Oh, so just like two-dimensional, what and all we feel as loop should be taken. That is a loop,
Yes, yes.
irrespective of it is being joined or not.
Suppose one more thing, one more precaution here. If it is open here, you cannot use it all.
Because that it doesn't form a closed loop.
Yes. But once it is closed, even though it is crossing, then it will be treated as a loop there.
And sir, one more thing, sir, regarding this loop direction that we are taking. Usually in the previous sessions and all, we never even considered about this loop direction anywhere.
No, in the examination, he will provide the loop direction.
Is there some sort of this thing, sir? Assumption sort of, or
no, nothing assumption. He specify in the question. He will specify in the question loop direction.
My doubt is, what is the significance of that loop direction? Like, what will happen if you just reverse it? Only this sign is going to change.
Sign is going to change. Nothing more than that.
Oh. I think that's it, sir. Thank you, sir.
Okay, but
Sir.
Swain.
Sir, if it is closed, then it will be 0. And see, if that is a small part is open, then it will be 0. That EMF.
No, how it is 0 if it is open. If it is open, then you can apply. You can't apply the Ampere's law. Okay, you need to go by the integration method.
Integration, okay. We can't say. Okay.
That's the thing.
Yes.
Avinash.
Hello, sir.
Yes, beta.
Sir, slide number 225.
Slide number
225, sir.
225, yeah?
Yes, sir. Yes, sir. Sir, here the H is equal to K by 2 into N vector. Have you got, sir?
That is the formula.
Okay.
This is the formula.
Okay, sir. Okay, sir.
That I will give an explanation here.
Sir, slide number 236. Okay, sir. Got it, sir. Sir, slide number 236. Sir, here I have not got, sir, this problem. So once, please
what these limits are indicating?
Sir, the range of 5.
If 3 coordinates are changing. If 3 coordinates are changing, then it is a volume. 3-dimensional. It is a volume.
Yes.
If it is a volume, then what is it indicates what is called a net flux. Net magnetic flux. Net magnetic flux is equal to 0.
Okay, sir.
Observe the previous question limits and these limits. So that you see, these limits are, here it is fixed 5.
Yes.
Yes.
Sir, is there any one should be fixed in this, or is there any condition, sir? That
nothing fixed here. 3 are varying. So it indicates something like a closed surface of some shape.
Okay, sir. So that's why we have got 0 here. Okay, sir. Sir, means one should be constant among 3.
If it is if it is one of the coordinate is constant, then it indicates the surface. So surface means what? There will be a flux, magnetic flux. Net magnetic flux is 0 according to the Gauss law.
Okay.
That is the thing. Any more questions? Okay, then I'll going to close the session. Bye, friends. Good night. Take care. Bye, friends.
Hello, sir.
Ah,
Sir, the same slide, last slide, sir. Last problem.
ah.
Sir, if this loop is not overlap, sir,
Ah.
suppose this, sir, the fourth one, the fourth loop, we have got, sir, the above the this eye, right side eye, then it will cancel, or what happens, sir?
What? Come again.
Sir, the fourth loop, suppose this will not overlap here, and the dot I is inside the loop, then is it cancels, sir, or not?
If it is not overlapping, two things you are saying, right? Let me draw what you are saying. One
Sir,
thing
the
is if
fourth
the
loop only.
huh?
Sir, the fourth one only.
Fourth
Here
one.
we have reversed, sir, for this.
If I reverse this one, what happens? It will become minus I. It will become 3I.
Sir, sir, no, sir, not that direction. The fourth loop, sir. We have taken here overlap, no, sir, fourth loop. So, sir, if we have not taken overlap it, and only the I is included in that. Yes, sir.
If it is not overlapping, then there is no meaning for the question. If they are touching here. Then you need to find out the MMF in this loop separately. In this loop separately. In this loop separately. There won't be any EMF, MMF in the overall loop. This is not an overall loop.
Okay.
It is a connection of 4 loops. Here there is the overall loop. There is a single loop, but here it is rotated 3 times. Here 1 time.
1 time. Sir, here the fourth one we have reversed, sir. Rotated, reversed it.
Fourth one, if we reverse this one, that will become minus. That's all it is.
That's what I am asking, sir. Actually. Then it will cancel, sir. Means I cancel.
What cancel out?
Sir, these both eyes will cancel, or the resultant. What will be the resultant MF then, sir?
One is?
What will be the resultant MF, sir? The final MF value? What will be?
Do you want me to reverse this current?
No, sir. No, sir. Not that current, sir. The fourth loop, sir, only. We have taken, sir, this from bottom. It will, if we touch, sir, from the top of the eye.
Do you want me to reverse this one? Which one you want me to reverse? Loop direction or current direction? Which direction?
No, sir, direction, not sir, direction. The bottom part of the fourth loop, sir, we have taken the upper end of upper side. Only that, sir.
How can you change that one up? Only that one. Because this is connected like this. See. How can I change only this one? Only if I reverse this one. If I reverse this one.
If, sir, I am asking, sir, that connection, sir, if like yours, sir.
All they are a single loop, that is. If I make this one down, then this one will be, this one should also be down. This one should also be down. This one should also be down. And so on.
Okay, okay, sir. Fine, sir. No problem.
That is the thing.
Okay, sir.
Okay, then I'll go on to close the session. Okay, then I'll go on to close the session. Take care. Good night.